Okay, so back with laws of large numbers. So what is expected value? Expected value is just a fancy way of saying the mean, or what you would normally call the average in probability courses that you've already taken. If you think back to elementary school, you probably talk about the mean, median, and mode. The mean is basically what we're talking about with the expected value. So basically, it's uh, if you assign a value to each of the most basic outputs and add them up times the probability, then you would get the expected value. So to give a pretty natural example, if I have a D6, um, there, there are infinitely many ways that I could assign values to these numbers, but I'm going to go with the obvious one of each number is weighted with its own value. So what should I expect? Well, if I would get 1/6 times 1 plus 1/6 times 2 plus 1/6 times 3 plus 1/6 times 4 plus 1/6 times 5 plus 1/6 times 6. So that's equal to 1/6 times I from I equals 1 to 6. So that should be 6 times 7 over 2 times 1/6. So this guy right here would be equal to 21 over 6 would be equal to 7 over 2. So I should expect 7 over 2 as my value that would pop out in this case. Heads and tails, there's two normal ways for us to assign these values. If we have heads equals 1 and tails equals 0, then we would have an expected value of is equal to 1/2 times 1 plus 1/2 times 0, which I trust you to figure out that is 1/2. And then the other way is if, say, you betting with a friend, if it's heads you get $1, if it's tails he gets $1. So then you would have this. So the expected value is equal to 1/2 times 1 plus 1/2 times -1 is equal to 0. So in this case, we would have expected value of 0. A lot of important things have expected value of 0. But it's something that you would expect any fair deal to have an expected value of 0, so that each person's taking on the same amount of risk reward benefit. If we have a process that towards okay, so if I have xi is my random process, so that's the thing that assigns the value based on if I get heads or tails, or if I get the or if I'm rolling the die, so whatever that process is. So then the sum from I equals 1 to n of xi over n, that tends towards the expected value of xi. So I'm repeating the same process over and over again. And that's just saying that if I repeat the same process over and over again, and then divide by however many times I'm doing it, it should tend towards that it will tend towards the expected value or the mean of the possible outputs. And the more formal way of saying this is that the probability that I get that I'm in the range of the expected value minus epsilon to the expected value plus epsilon tends towards 1. So that with probability 1, I will be within a very, very small range of my expected value. And epsilon is just an arbitrary small number. So if to give you guys an example, let's look at a random walk, and we'll do the xi is equal to 1 if heads and -1 if tails. So we branch out, we get heads, tails. So this is -1, 1, branch out again, and then I would get heads, this would be 2, 0. And this guy also gets me to 0. This guy gets me to -2. And these guys each branch up and down again, and it would be 1 or -1, 1 or -1. This guy can go down to -3 or can go up to -1. This guy can go up to 3 or can go down to 1. So if I were to examine these guys, then I have either 1 or -1. If I were to look at this level, then I would have probability of -1. -2 divided by 2, because I'm normalizing these guys. I'm dividing them by n. So that's equal to the probability of -1 is equal to 1/4. Probability of 1 is also equal to 1/4, and the probability of 0 is equal to 1/2. And if I look at the third generation, then what do I get? So I get the probability of 1 is equal to 1/8. Probability of -1 is equal to 1/8. And then the probability of 1/3 is equal to, it's going to be 3/8. And the probability of -1/3 is also going to be equal to 3/8. And if you just keep on iterating this process over and over again, you'll keep on getting things, your odds of it being within a small neighborhood of 0 are going to tend towards being guaranteed. That you'll have you'll always have these fringe things. You'll always have the possibility of getting 1 or -1, but that probability is going to tend towards 0. And kind of interestingly for this guy, because if I flip the coin an odd number of times, it's impossible for me to have gotten 0. I'll actually always have rounds where I won't be exactly at 0, but I'll be very, very close. So at this point, 1/3. At the next point, I'll have a bunch of 1/5, and so on. So t between 0 and m, then the probability that out of 2m. Yeah, so this is basically saying, so if I look at my first one, but I have the odds of getting 1 or -1 in the first generation. If I look at the second generation, then I have similar looking odds of getting 0, and then half that odds of getting 1. If I look at or I guess, sorry, I should actually have that at 2. 2 and -2. If I repeat the process over for 3, then I'll get this guy. Basically, what I end up getting tends towards looking like a normal curve, and that's what this is saying. So if I have if I were to normalize this guy, I would get what looks basically like a normal curve with with standard deviation 1, and then right here, this is spreading out the normal curve. So the normal curve with distribution 1 is just described by this probability of e to the negative t squared, or and then this is going to provide a slight upper bound for it being between these values, if this is m minus t. But that is going to be if we have I'm sorry, kind of disregard what I just said. The reason I was getting confused is that this proof is assuming that we have probability, or that if we get heads, then its value is 1, but if we get tails, then its value is 0 instead. So this isn't going to look like this. It's going to, where I have both sides, it's going to be equal. It's going to have a sliding value with the mean centered at m instead of centered at 0. So here the mean would actually be, or not the mean, but the m. So if I had 2m, then it would be the expected value of the mean flips. So my mean is going to be sliding as I go. It's not going to be centered at 0, but it's still going to look basically like a normal distribution. It's just going to be, and it's going to approach it, if we were to subtract m, it would approach a normal distribution as we go off to infinity. So